menyediakan wahana edukasi kepada semua bagian dari industri, mulai dari mahasiswa, fresh graduate, hingga profesional. Penasaran dengan dunia industri energi dan perkembangannya? Yuk, simak program-program dari kami. Gali ilmu praktisi bersama Enerka. Enerka merupakan platform digital yang berisi kursus online dengan fokus pada topik energi yang diisi langsung oleh praktisi energi di Indonesia. Di Enerka, kalian akan mendapatkan video materi, e-book untuk mendukung proses belajar, kuis di setiap bab, dan final test di akhir kursus. Dan tentu saja, kalian juga akan mendapatkan sertifikat setelah menyelesaikan kursus. Enerka memudahkan kita karena bahan belajar dapat diakses di mana saja dan kapan saja. Berkolaborasi dalam inovasi bersama Enerka. Enerka merupakan program yang bertujuan sebagai media kolaborasi dalam riset untuk semua kalangan, baik itu praktisi, fresh graduate, maupun mahasiswa. Enerka merupakan wadah yang cocok untuk kalian yang hobi menulis atau yang sedang ingin membuat karya tulis. Tidak sampai di situ saja, riset yang dilakukan akan dikembangkan menjadi paper atau karya tulis yang nantinya akan dipublish di konferensi atau workshop nasional maupun internasional. Mari lihat jendela dunia energi bersama Enershow. Enershow merupakan suatu rangkaian acara webinar yang sudah terafiliasi langsung oleh praktisi-praktisi energi di Indonesia. Dengan berkolaborasi dengan organisasi-organisasi kemahasiswaan, Enerka siap menyediakan webinar dengan topik yang diinginkan beserta praktisinya tanpa harus melalui proses birokrasi yang bertele-tele, alias cepat dan mudah. Belajar energi lebih dalam bersama Enerlight. Enerlight merupakan hands-on training yang diadakan oleh Enerka. Enerlight merupakan program training terjadwal di mana materi akan dibahas secara mendalam langsung oleh praktisi yang ahli di bidangnya. Fasilitas apa saja yang akan didapat? Berikut merupakan fasilitas yang bisa didapatkan dari mengikuti program training Enerlight. Mau tahu lebih lengkapnya? Yuk bergabung bersama kami. Stay tune terus di sosial media Enerka agar selalu mendapatkan update terkini terkait acara-acara di Enerka. Enerka, gali ilmu praktisi. Hai Ener Friends, selamat datang di Enerka. Platform edukasi energi berbasis teknologi pertama di Indonesia. Bersama-sama, kita meningkatkan kompetensi anak bangsa dalam rangka mendukung perkembangan proyek energi di Indonesia. Menyediakan wahana edukasi kepada semua bagian dari industri, mulai dari mahasiswa, fresh graduate, hingga profesional. Penasaran dengan dunia industri energi dan perkembangannya? Yuk, simak program-program dari kami. Gali ilmu praktisi bersama Enerka. Enerka merupakan platform digital yang berisi kursus online dengan fokus pada topik energi yang diisi langsung oleh praktisi energi di Indonesia. Di Enerka, kalian akan mendapatkan video materi, e-book untuk mendukung proses belajar, kuis di setiap bab, dan final test di akhir kursus. Dan tentu saja, kalian juga akan mendapatkan sertifikat setelah menyelesaikan kursus. Enerka memudahkan kita karena bahan belajar dapat diakses di mana saja dan kapan saja. Berkolaborasi dalam inovasi bersama Enerka. Enerka merupakan program yang bertujuan sebagai media kolaborasi dalam riset untuk semua kalangan, baik itu praktisi, fresh graduate, maupun mahasiswa. Enerka Enerka merupakan wadah yang cocok untuk kalian yang hobi menulis atau yang sedang ingin membuat karya tulis. Tidak sampai di situ saja, riset yang dilakukan akan dikembangkan menjadi paper atau karya tulis yang nantinya akan dipublish di konferensi atau workshop nasional maupun internasional. Mari lihat jendela dunia energi bersama Enershow. Enershow merupakan suatu rangkaian acara webinar yang sudah terafiliasi langsung oleh praktisi-praktisi energi di Indonesia. Dengan berkolaborasi dengan organisasi-organisasi kemahasiswaan, Enerka siap menyediakan webinar dengan topik yang diinginkan beserta praktisinya tanpa harus melalui proses birokrasi yang bertele-tele, alias cepat dan mudah. Belajar energi lebih dalam bersama Enerlight. Enerlight merupakan hands-on training yang diadakan oleh Enerka. Enerlight merupakan program training terjadwal di mana materi akan dibahas secara mendalam langsung oleh praktisi yang ahli di bidangnya. Fasilitas apa saja yang akan didapat? Berikut merupakan fasilitas yang bisa didapatkan dari mengikuti program training Enerlight. Mau tahu lebih lengkapnya? Yuk bergabung bersama kami. Stay tune terus di sosial media Enerka agar selalu mendapatkan update terkini terkait acara-acara di Enerka. Enerka, gali ilmu praktisi. Hai Ener Friends, selamat datang di Enerka. Platform edukasi energi berbasis teknologi pertama di Indonesia. Bersama-sama, kita meningkatkan kompetensi anak bangsa dalam rangka mendukung perkembangan proyek energi di Indonesia. Menyediakan wahana edukasi kepada semua bagian dari industri, mulai dari mahasiswa, fresh graduate, hingga profesional. Penasaran dengan dunia industri energi dan perkembangannya? Yuk, simak program-program dari kami. Gali ilmu praktisi bersama Enerclass. Enerclass merupakan platform digital yang berisi kursus online dengan fokus pada topik energi yang diisi langsung oleh praktisi energi di Indonesia. Di Enerclass, kalian akan mendapatkan video materi, e-book untuk mendukung proses belajar, kuis di setiap bab, dan final test di akhir kursus. Dan tentu saja, kalian juga akan mendapatkan sertifikat setelah menyelesaikan kursus. Enerclass memudahkan kita karena bahan belajar dapat diakses di mana saja dan kapan saja. Berkolaborasi dalam inovasi bersama Enerclub. Enerclub merupakan program yang bertujuan sebagai media kolaborasi dalam riset untuk semua kalangan, baik itu praktisi, fresh graduate, maupun mahasiswa. Enerclub merupakan wadah yang cocok untuk kalian yang hobi menulis atau yang sedang ingin membuat karya tulis. Tidak sampai di situ saja, riset yang dilakukan akan dikembangkan menjadi paper atau karya tulis yang nantinya akan dipublish di konferensi atau workshop nasional maupun internasional. Mari lihat jendela dunia energi bersama Enershow. Enershow merupakan suatu rangkaian acara webinar yang sudah terafiliasi langsung oleh praktisi-praktisi energi di Indonesia. Dengan berkolaborasi dengan organisasi-organisasi kemahasiswaan, Enerka siap menyediakan webinar dengan topik yang diinginkan beserta praktisinya tanpa harus melalui proses birokrasi yang bertele-tele, alias cepat dan mudah. Belajar energi lebih dalam bersama Enerlight. Enerlight merupakan hands-on training yang diadakan oleh Enerka. Enerlight merupakan program training terjadwal di mana materi akan dibahas secara mendalam langsung oleh praktisi yang ahli di bidangnya. Fasilitas apa saja yang akan didapat? Berikut merupakan fasilitas yang bisa didapatkan dari mengikuti program training Enerlight. Mau tahu lebih lengkapnya? Yuk bergabung bersama kami. Stay tune terus di sosial media Enerka agar selalu mendapatkan update terkini terkait acara-acara di Enerka. Enerka, gali ilmu praktisi. Hai Ener Friends, selamat datang di Enerka, platform edukasi energi berbasis teknologi pertama di Indonesia. Bersama-sama, kita meningkatkan kompetensi anak bangsa dalam rangka mendukung perkembangan proyek energi di Indonesia. Menyediakan wahana edukasi kepada semua bagian dari industri, mulai dari mahasiswa, fresh graduate, hingga profesional. Penasaran dengan dunia industri energi dan perkembangannya? Yuk, simak program-program dari kami. Gali ilmu praktisi bersama Enerka. Enerka merupakan platform digital yang berisi kursus online dengan fokus pada topik energi yang diisi langsung oleh praktisi energi di Indonesia. Di Enerka, kalian akan mendapatkan video materi, e-book untuk mendukung proses belajar, kuis di setiap bab, dan final test di akhir kursus. Dan tentu saja, kalian juga akan mendapatkan sertifikat setelah menyelesaikan kursus. Enerka memudahkan kita karena bahan belajar dapat diakses di mana saja dan kapan saja. Berkolaborasi dalam inovasi bersama Enerka. Enerka merupakan program yang bertujuan sebagai media kolaborasi dalam riset untuk semua kalangan, baik itu praktisi, fresh graduate, maupun mahasiswa. Enerka merupakan wadah yang cocok untuk kalian yang hobi menulis atau yang sedang ingin membuat karya tulis. Tidak sampai di situ saja, riset yang dilakukan akan dikembangkan menjadi paper atau karya tulis yang nantinya akan dipublish di konferensi atau workshop nasional maupun internasional. Mari lihat jendela dunia energi bersama Show. Show merupakan suatu rangkaian acara webinar yang sudah terafiliasi langsung oleh praktisi-praktisi energi di Indonesia. Dengan berkolaborasi dengan organisasi-organisasi kemahasiswaan, Enerka siap menyediakan webinar dengan topik yang diinginkan beserta praktisinya tanpa harus melalui proses birokrasi yang bertele-tele, alias cepat dan mudah. Belajar energi lebih dalam bersama Enerlight. Enerlight merupakan hands-on training yang diadakan oleh Enerka. Enerlight merupakan program training terjadwal di mana materi akan dibahas secara mendalam langsung oleh praktisi yang ahli di bidangnya. Fasilitas apa saja yang akan didapat? Berikut merupakan fasilitas yang bisa didapatkan dari mengikuti program training Enerlight. Mau tahu lebih lengkapnya? Yuk bergabung bersama kami. Stay tune terus di sosial media Enerka agar selalu mendapatkan update terkini terkait acara-acara di Enerka. Enerka, gali ilmu praktisi.
Assalamualaikum warahmatullahi wabarakatuh. Good morning and warm greetings to everyone. Honorable speakers joining us today, Mr. Scott Herman and Mr. Stephen Sewell. Distinguished representative of AP Jun 4 SI, Ms. Safina Alia Farhani, and our dear participants who have taken the time to join us for this webinar today. Let us begin by expressing our gratitude to God Almighty, for it is by His blessings that we are able to gather here today, even though this session is conducted online. Allow me to introduce myself. I am Anissa Umayra Ramadanti, and I have the privilege of serving as your Master of Ceremony for today's webinar. This morning, we will delve into a discussion topic. First, the unconventional geothermal system around the world. Before we begin, let me walk you through our agenda for today. First, there will be an opening remarks. Second, welcoming speech by Ms. Safina Alia Farhani. Third, introduction to Enerka. Fourth, presentation of materials. Fifth, Q&A session. Sixth, memento ceremony. And the last one is photo session and closing. Without further ado, let us commence this webinar. I hope you find it both insightful and inspiring. Let's begin. Next, we will have the honor of hearing a few words about welcome from representative of APG Patesi. To Ms. Safina, the floor is yours.
Thank you, Anissa, for the time. Greetings. Good morning, ladies and gentlemen. My name is Safina Farhani. I am the president of APG SE 2025. Here, thankful for this opportunity with Team Enerka in this collaboration towards success for the unconventional geothermal systems around the world. To our distinguished speakers, Mr. Scott Herman and Mr. Steven Sewell, I humbly appreciate your time for today's event. I hope this course will be an output towards wider and deeper knowledge to us all. That is all from me. I won't want to postpone another second to learn today. Thank you. I'll hand it over to Anissa again.
Thank you, Ms. Safina, for the warm and insightful opening remarks. As outlined earlier, we will now proceed with a brief presentation about Enerka. To Tracy from Enerka team, the time is yours.
Okay, hello everyone. For Anissa, my sound clearly heard.
Yes.
Hello.
Yes, we can hear you.
Okay, so sorry for the bad connection here. Well, everyone, let me introduce. Okay, sorry. Here. I want to introduce myself first. My name is Tracy Maria. I'm from Enerka, or PT Enerka Bumi Pratama, and we also known as Enerka. So we are the first education platform in Indonesia by focusing in sustainable and renewable energy. So for now, we already conducted 230 trainings, which serve 10,000 participants in total, and we're established since March 2020. So basically, we are at South Jakarta at Sedimentary Tower, 11th floor. Okay, so what we usually do in Enerka, we have several education programs. So we provide interaction and collaboration between practitioners, graduate students, and also the academics in the energy industry. So the first one, we had Anon class. What is Anon class? Anon class is a web-based online course focusing on various energy topics with an easy enrollment process, and it can be accessed anywhere with flexible learning completion time. So maybe later I will give the website here, the link on the chat box. And then the second one is Analyte. Analyte is another life training on energy. So we provide for students and also professional with topic discussed in total 8 until 12 learning hours. and it's held in 2 or 3 days. So it's separate in 2 or 3 days. And then the next one is Enerka, which is held today and now. It is a free webinars and open to the public, and it will be a collaboration with a student organization, and we discuss about various energy topics. Like now, we focus on unconventional energy, and this webinar is recorded live through a YouTube channel and is accessible at all times. And the next one is Enerka. And a club is a club that facilitates collaboration between practitioners and also students. So in this club, we conduct research that results in publication. And then for the next one is in-class training. So in-class training is an offline educational program. Also in this training is conduct offline, so there will be an in-person training experience, and also it covers key topics over 8 until 12 hours in separate 2 or 3 days, providing interactive learning opportunities with the experts. So maybe that's all from me. I will give it back to Anissa. Thank you, Anissa.
Okay, thank you, Tracy. I will now hand over to our moderator, Serena from GeoEnergis.
Okay, thank you so much, Anissa. So hello everyone. As Anissa mentioned before, I am Sarina that will be a moderator for today's webinar. It's very exciting that we can learn something new directly to our expert in geothermal industry. So before we start the presentation, let me introduce our speaker today. Okay. For Enerka team, maybe can help to share the screen. Okay, so for today's webinar, we have two experts for sharing his knowledge and insight regarding the unconventional geothermal system. The first speaker is Scott Herman. Scott Herman was a senior geologist in GeoEnergis. And the second speaker is Stephen Sewell. He is a senior geophysicist in GeoEnergis. Okay, due to the technical issue from our side, so these presentations have 1 hour durations. For all the participants that have questions while the speaker present their material, feel free to write it on the chat box. So after the presentation material on the Q&A session, we'll open discussions. So you can ask directly your questions, or I will help to read your questions. Okay, without further ado, maybe I would like to say hi to Steve and Scott. Hi, Steve. Hi, Scott.
Hello.
Hello.
Hello. I think in Scott area, it's already evening. So without further ado, the time is yours, Steve and Scott.
Okay. Hi, my name is Scott Herman. I'm a geologist and geochemist. I've been working in the geothermal industry for about 15 years, and I've been a geologist professionally for about 20 years. Before geothermal, I worked in mineral exploration and marine geology. And I started my career with Geothermex back in 2009, and since then I've worked in the US and New Zealand and Indonesia, a number of other countries. Can you hear me okay? And I've worked on a variety of fields, both as a consultant and for operators.
Yes, Scott.
Sorry. Can you hear me, or should I start over?
Yeah, I think we can hear you okay, Scott.
Okay, sure. There we go. Cool. Anyway, I've worked for a variety of companies here, and Steve and I have even worked for the same company, although we didn't overlap in time, but that's how we met. So my expertise is largely in geology and geochemistry with a smattering of geophysics, but Steve has a much better understanding of geophysics than I do. And I'm gonna walk us through EGS systems, and then Steve is going to talk about sedimentary basin systems. We'll talk about a few other things as well, but we kind of agreed that we think that these are the most likely to succeed in the short term, alternative or unconventional geothermal resources. So we thought we'd focus on those today. And I'm perfectly happy if people have a question to chime in, put it on the chat. I'll try to answer it as we go, and if I don't get it as we go, we'll follow up with it later. Steve, would you like to introduce yourself?
Yeah, sure thing. There I am. Yeah, so I'm a geophysicist, about 20 years experience in geothermal now, and have worked on a range of projects from early exploration through to exploration drilling, development of fields, and in operations as well. I first started in Australia, and they were very big on unconventional resources back in 2010 when I was leaving university. So my first work experience was actually on unconventional resources, particularly sedimentary basin resources. But since then, I went to New Zealand and worked there for 5 years, did a PhD whilst I started a consulting company as well. And I've now worked in quite a lot of countries on all of the continents except for Antarctica now. All right, that's me. Okay,
we dive into it, or do we have an intro first?
Okay, now we will enter the presentation material from our speaker. So Stephen and Scott, the time is yours to present the material.
Okay. All right, welcome folks. It's nice to have you all here. Thank you for taking the time to be with us today and to listen to what we have to say. Hopefully we can shed some light on some of the practical aspects of conventional geothermal systems, and maybe flesh out a little bit what you learned in school. Okay, this is all right. So I'm going to go through EGS for about half an hour, a high-level description of EGS, talking about a little bit about the best potential areas, and then some examples of past and current projects, and some discussion of challenges. And I think Steve will chime in a little bit on these too. He's had some experience with some of these particular projects. And then we'll talk about the potential for this technology in Indonesia. And then Steve will have another 30 minutes. You want to just run down the quick description there, Steve?
Yeah, it's essentially the same kind of topics as what Scott's going to talk about. Yeah.
All right, this is asking me to confirm my speaking language, and it is not Bahasa, like you can probably imagine.
Do you want me to go through this one, Scott? Or?
Sure.
I don't know if I've got a pointer here, but
All right.
So we thought we'd just give a bit of a geothermal 101, just in case participants aren't that familiar with geothermal. So the way I like to think of it, and a lot of other people think of it, is really as a process of heat mining. You're mining heat from the rock, and so you're taking fluid out of the ground in production wells. That's the heat comes from the rock and the fluid in the rocks. We take that heat and transform it to electricity in the power plant, and then the cooled fluid goes back down into injection wells. And this is kind of a picture of or cross-section of a typical andesite volcano resource, such as would be found in Indonesia. So you've got down deep, you've got heat and gas coming up from magma. The reservoir usually consists of fractured rocks, and fluid, the hot fluid buoyantly flows up to the top of a cap rock. And there it can flow laterally out to hot springs, or it can make its way to surface as fumaroles. So heat for most of the conventional geothermal systems, the heat comes from either magma or from deep circulation. There's a lot of systems in the US that are actually circulation of fluid along permeable faults down deep and then coming back up. And the vast proportion of current geothermal capacity is convecting systems now. This basically means that fluid is circulating, moving up and down within the system, and so that makes the temperature within the reservoir isothermal. So you can see that the gap between the 200 degrees Celsius isotherm and the 300 is quite large. So it's distributing the heat within that volume of rock. Geothermal systems are essentially heat and permeability anomalies. They don't occur everywhere. They're geographically restricted volcanic areas, and where permeability allows structures and structural geology. So the idea that's been around for some time, at least extending back to the 70s, is how can we expand the use of geothermal and not have it be just in geographically niche areas. So the main ones that have been looked at and we'll discuss today EGS, or Enhanced Geothermal Systems, and sedimentary basins. And these unconventional resources mostly aim to extract heat from conductive systems. So this is, instead of convective systems where fluid's moving around, you've got conductive systems where the temperature increases linearly with depth, and that's because there's not a lot of vertical permeability, not a lot of flow through fractures up and down. But yeah, just one last point on that. You know, the attraction of these resources is that they're much more widespread and they have vast thermal energy potential. So next slide. Scott, do you want to do this one?
I'll speak to this and a couple points about the last slide as well, which is basically that the systems that have been developed so far, particularly in Indonesia, but in most of the world, are these convective hydrothermal cells, right? You have a combination of shallow heat and permeability that allows for the formation of a convecting cell. The way I like to think about it is that the reservoir is a big thermal battery that's been charged up by a trickle charger from the bottom, and the whole reservoir ends up, as Steve said, isothermal. It basically ends up at the temperatures associated with the bottom. And so that brings deep temperatures up shallow where you can get at them. And the very permeability that allows that system to form also allows us to extract heat from it. Because, as Steve alluded to earlier, in geothermal, it's tempting to think of the fluid as a resource in the same way as oil, but it's not, in the sense that it's really just a working fluid for extracting the heat. Once it loses the heat, it doesn't really have much value. So you can't put it in a barrel and ship it off somewhere else in the world and sell it. So we use that same fluid, we put it back down into the reservoir on the margins, and then let it reheat and keep cycling it through as a way of extracting the heat. And those systems are what we have developed so far because they create this particular circumstance where the heat is both relatively shallow and therefore less expensive to get to, and relatively easy to extract because the permeability is already there. The downside of those systems is that they're very geologically unique. As we say in English, you have to get a lot of ducks in a row to get these systems, which is to say you have to have a combination of all the right geologic circumstances for these systems to exist and then persist. You need this vertical permeability that the very systems that, the geothermal systems themselves will start to plug up the permeability over time. And so you need it to be tectonically reactivated. So you really only get these systems in these sort of plate margin areas, a few other places, but they're quite geographically limited, which is why, on the one hand, geothermal is great. And on the other hand, as a global energy source, it's a fraction of a percent. And Indonesia is unusual in this case in that because Indonesia is on the ring of fire, you've got geothermal resources all over the place. Whereas if you look at, say, the continental US, we've got great geothermal resources, but they're almost all in California and Nevada, and hardly any of them are anywhere else in the rest of the country, a little bit in Alaska. Anyway, the trick here with unconventional systems is the idea that the background geothermal gradient, which is the conductive geothermal gradient, which is everywhere on Earth, heat is pouring out of the center of the Earth towards the crust. And it varies a little bit from region to region, depending on the thickness of the crust and different things, but it's everywhere. So it's an immense resource, but it's much harder to extract the heat because it doesn't have that vertical permeability necessarily naturally sitting there that forms these convection cells. So the heat is typically deeper and the heat is typically harder to extract because you have to create the permeability or enhance the permeability somehow to get it out. In some cases, permeability is already there in some of these sedimentary basins, but it's largely lateral and not vertical. So lateral permeability can be used to extract heat, but it doesn't form convection cells, or much of a convection cell. The vertical permeability is required for that. So as we get into unconventional geothermal systems, it's an attempt to figure out how to get into a vast resource where we're getting into the sedimentary basin systems and hot dry rock systems and even super hot rock systems, although that as yet is more of a research topic than a reality, but we hope to get there. And the appeal of these is that if we can figure out how to do this economically, we kind of know how to do it technically, but it's one thing to do it in a small test. It's one thing to do in the lab, and then it's another thing to take the lab and recreate it in real life. And then it's yet another challenge to scale it up to a utility size project. And finally, to make it cost effective so you actually make money. All of those stages are significant technical challenges. And that is what we're working through with these unconventional resources. And to varying degrees of success with different types of resources. So I find this figure very useful because think back earlier, we talked about convection cells. If you look on the left, this is a linear conductive geothermal gradient. It gets hotter as you go deeper. This is happening everywhere in the world, and the slope of the line is a little different depending on where you are. When you get a convective system, what you have here is what you have in the right-hand side of this. Within the reservoir where the arrows are circling, that whole body of rock heats up to the temperature associated with 10,000 degrees. See that? And so, or sorry, with 10,000 meters. Or sorry, is this in feet? Yeah, all right, 10,000 feet, my bad. But the point still holds, is that that temperature associated with 10,000 feet propagates all the way up to something like, 3,000 there. And that whole body of rock, which takes a long time to come up to that temperature, it sort of charges slowly like a big thermal battery on a trickle charger, is then available for us to extract, and you only have to drill to 3,000. When you're trying to get into the conductive resource, like on the left, you have to drill deeper, typically to get to the same temperatures. So in that case, you got to drill to 10,000 feet to get to, what temperature is that? 525, let's say. And here on the right, you can see a variety of these straight lines are a variety of conductive gradients. And then like here on the far right, on the top right, you can see Larderello, Italy. This is a steam field. This is the definition of a convective geothermal resource. See how the green line goes out to the right? You can get to high temperatures, very shallow. They're largely isothermal. Well, I guess that's following the boiling point to depth curve at that point. But you can see how that's much more attractive to try to drill into because it doesn't require as much drilling to get to those temperatures. But as we said, those resources are quite rare. And so we're trying to figure out how to learn to economically extract these resources that are on the left, that are the sort of blue and red and purple lines. Okay, next slide. Okay, so these are kind of key questions that you would ask yourself when looking at a geothermal prospect. When they say, what is the hypothetical geothermal play? I mean, what type of geothermal system might it be? Is it a convective system? Is it a volcanic convective system? Is it a fault-hosted convective system like you see in Nevada or in Western Turkey? How hot is it? How permeable is it? What are the fluid qualities? Are they benign, or are you going to have to do a lot of work to adjust the chemistry to not cause problems in the plant, such as scaling or corrosion, things like that? And then how big is the resource? Because all of these questions together kind of get at whether or not this thing is worth pursuing as a commercial project, which is a different question than whether it's worth pursuing as a research project, which, some of the unconventional resources at this point are still more in the research stage than they are in the commercial stage. You want to say anything else about this, Steve?
No, not really. I'll just add that, these are the things that you're looking for when you're doing exploration of a field as well. It's, finding sufficient temperature, finding sufficient permeability, finding fluid that is benign. Once you have those three, then it's, it's about how big it is. and how big it is really determines the size of the development you can do, and plays a lot into the economics of the project.
And one thing that this map illustrates very nicely is, we mentioned that the conventional convective systems that have been developed thus far economically are really limited to these little colored spots. But you can see that most of the world is the gray that is not highlighted by those. And that's what we hope to open up using unconventional geothermal systems, is all the gray areas may become progressively appropriate for geothermal development if we are able to figure out how to do these unconventional geothermal systems economically. And that's a lot of potential, because it's a lot more area. Okay, next slide. Excuse me. Okay, what is enhanced geothermal system? So there's sort of two ways to look at this. One is, so early on in the idea of an enhanced geothermal system is they had an existing convective resource that maybe wasn't spectacular, or you got a well into a marginal part of the resource that wasn't that great. And they were particularly interested in, how can we improve the permeability in these wells? And for context, when we talk about the things that you need to have a geothermal system, particularly a convective geothermal system, the biggest two are heat and permeability. And permeability is almost always the limiting factor there. It's more common to have heat than it is to have permeability, and heat tends to distribute itself a little bit more evenly than permeability, which is to say that permeability can vary wildly in the subsurface. You can have a very permeable well right next to a relatively impermeable well, followed by another very permeable well near that. And that's kind of I would say it's sort of the holy grail of geothermal, and frankly, other subsurface things, other subsurface disciplines. It's very hard to predict permeability accurately. And what would happen is, if it wouldn't be uncommon to drill wells that were hot, but not very productive. And so the idea was to start to basically enhance those fractures in the well and create more permeability. That idea in the early days had a lot of challenges to it. And one of the challenges is that, unlike oil and gas fields, which are basically closed systems that are tight, and so you can inflate them and fracture them fairly efficiently, geothermal systems always have, here you can see on the left in the figure, they always have a leak where the hot springs come out, and they need that leak to stay alive. So if you look on the left of the figure there, where the hot springs are, these systems are always a bit leaky, but it also makes them a little bit more challenging to fracture, because it's sort of like trying to blow up a leaky balloon. It can be, it can take a lot of frac trucks or pumps or whatever to try to do that. And early efforts into that there was some success, but it wasn't as successful, I think, as people hoped. And people sort of moved away from that in-field improvements to going into near field, trying to create permeability connections sort of in the conductive halo around fields. So this is what Fervo was doing at the Red Project in Blue Mountain. If any of you have read about this in the last few years, they started drilling into the non-permeable rocks that are around a convective and permeable hydrothermal system, that were heated to temperatures, because they were next to the hydrothermal system, higher than they would have been at those depths. And so they were trying to sort of improve the recovery of the field by mining the extra heat. And it was a little bit easier to frack because the rocks shouldn't say easier to frack, but they know how to frack it better, because the rocks were impermeable to start with, and so they could control it a little bit better. And then there's the idea of creating these deep standalone sort of, there's no hydrothermal system around, and you can just go but there's deep hot rocks and you can frack them. And I would argue that Fervo, I don't know if I would agree that they're completely deep standalone. I mean, in one way they are, and in one way I would call them near field. But it's basically because both in the case of Fervo and Google, they are adjacent, or they are adjacent to convective hydrothermal systems, but they're in the rocks that are impermeable. But the whole idea of EGS is to try and create permeability where there wasn't any before. And once you've created that permeability, you can sweep the water through and extract heat from what was the conductive geothermal background. And so you can do this by hydraulic fracturing, which is what I was referring to earlier, where you get these big pumps and you inject water and you inject sand usually, or some other sort of proppant, that when the fractures open, the sand rushes in and then it holds them open when you reduce the water pressure. Acid injection, which basically the conductivity is, well, the acid goes in and etches away minerals such as calcium carbonate and others that and then the sort of the roughness left on those fractures can keep them open. That's also called an acid job often. And then thermal fracturing actually is really effective. As you're injecting cool water, the rocks contract around that, and that will actually create some fairly far-reaching fractures. And often hydraulic fracturing and thermal fracturing are happening together, because you'd be injecting with cold water. These resources here, where they talk about on the right, like Raft River and Soda Lake, those were higher temperature resources, more what I'm talking about the early days, and they had some success with those. And I used to work, when I worked at Geothermex, they were working on Desert Peak and Brady's in Nevada. Again, they had some success with these, but to be honest, it wasn't great, which is one of the reasons that they tried a lot of different things over a number of decades, and they definitely improved things, but for the amount of money it cost them, it wasn't really considered a huge success, I would argue. And this is sort of what it's led us to looking more at these Fervo and Google type resources. And also these two at the top, these sort of in-field and near-field, they still suffer the same problem as conventional resources, which is if you're either trying to improve a conventional resource or slightly enlarging a conventional resource, you're still constrained by the occurrence of conventional resources, which is limited, as we said. Whereas these deep standalone type projects, which right now are kind of being done in a more near field way, but the idea is to get the technology to the point where it's economic to do it anywhere. And I want to stress that if and when that happens, that would be a game changer for the global energy picture. That would take geothermal, like right now, if we manage to double the geothermal industry globally, we go from 0.5% to 1% of the global energy picture. If we can manage to get these deep standalone projects, to be economically viable, that will, I think, fundamentally change the global energy picture. Would you agree with that, Steve? It's sort of seems to me anyway.
I think there's definitely that potential, and I think one of the main reasons why is because geothermal is base load. It runs 24/7. and our other renewable options that we have don't run 24/7. So there's really a need for that base load power, and yeah, it would be cool if geothermal could provide it.
Right. I see it as there are still significant barriers. We're working hard on this, and we've made progress, but there are still significant barriers. But the potential upside is so high that it's really I think it's worth pursuing, even when it sometimes gets a little discouraging that we're not moving faster, or that it's still expensive to do. Okay, next slide. So global best locations for EGS are, you're still looking, it still works best where the heat is shallowest. Fundamentally, drilling is expensive, and the deeper you go, the more expensive it gets, and it tends to be exponential rather than linear. So if you can get in areas where the best areas for EGS are going to be where it's hottest, and then they'll sort of where it's hottest and where it's easiest to fracture the rocks and hold those fractures open. So the first thing you want to do is without high heat, there's not much point in doing it, because it'll be hard to pay for itself. So obviously the plate margins where current convective systems already exist are, probably are among the most attractive. But you can also see these are there's more of this than there is of actual convective geothermal systems, which is to say that you could, like, a good example of this is the Salton Trough. The Salton Trough is where the Salton Sea geothermal field is. It's in Southern California. If you go up to the west coast of America here, a little further north, see where that red line goes into the western margin of North America. So the plate boundary. I don't think you can see but where the highlighter is at the moment, up and to the left of there, it's basically where the San Andreas Fault comes down into the Gulf of California. That excuse me, that structural trough is the home to a number of very prolific geothermal fields, some of the most prolific geothermal fields in the world. But the entire trough is like 3 times the average global geothermal gradient. So anywhere in that basin, from a heat standpoint, would be an attractive place to look at EGS, even though within it there are only certain places that are actively convecting hydrothermal systems. But you can see the distribution of this is a lot wider, and Indonesia is sitting on a whole bunch of hot, like everything in Indonesia is basically somewhat hot. So that's very attractive for Indonesia. Next slide. Or do you want to add anything to that, Steve? Okay, next slide. Oh yeah, so this kind of speaks to what I was talking about before. There's massive demand, particularly for base load energy. The US, this is the case of the US, and renewable energy consumption is a tiny fraction of it. And so there's a huge market here for if we can make it economic, there's definitely a demand for it. And so it's really just a question of figuring out how to make it economic. And I would argue that at least the figures that I've seen in the past, geothermal energy is more like 0.5% of US energy consumption. Maybe it's gotten better, but it's tiny. Excuse me. Okay, next slide. So you can see, even though California, So basically down here in the bottom of California, that's the sort of Salton Sea area to the left, further to the left, where this black line comes down, 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 follow that black line to the bottom. Right down there, that's the Salton Sea area. But California, all along the coast there has high potential, and then the western US has a lot of high potential. And you can see a lot of the US is fairly low potential, which basically means you just have to drill fairly deep to get to the high temperatures, which makes it, more expensive. Indonesia is, I think, basically all high potential. I wish we had a map of that, but anyway, let's see what else we got. Next slide. Okay, so can we go back to the last slide for a second? So this whole no, you were keep going backwards, back to the big map of the US. There you go. This whole red area in the western US, most of this is high potential because the crust there has been pulled apart by extension and is roughly half as thick as normal continental crust, which means that the background geothermal gradient is roughly twice as high. And that's why we get a lot of these deep fault circulation systems there, because there's very extensional faults with high fluid flow that penetrate very deeply, and it allows it to go down into rock that is quite hot because the crust has been thinned and the magma is relatively shallow there. So next slide, if you go to Utah Forge. So this project, the Utah Forge project, is sited in that region. It's called the Great Basin in the US, or also known as the Basin and Range. And this is a research and development project funded by the US government, and where they are near some known geothermal resource areas. You can see that the Blundell geothermal power plant at Roosevelt Hot Springs is near there. But it's basically non-permeable granites that they've been drilling into. And the whole focus of it is, if you think about geothermal globally, one of the challenges that we face is we use, for example, oil field drilling technology, largely slightly adapted to geothermal conditions. Oil field drilling technology has been optimized for the geologic conditions that oil is mostly found in. So it's really been optimized around sedimentary, sort of pancake layer cake rocks. And if you've drilled in those type of rocks and then gone and drilled a well in Indonesia, you're like, oh man, it takes a long time to drill in volcanic rocks compared to sedimentary rocks. It's much slower going. And part of this is just that volcanic rocks are harder. But part of it is a question of what the tools were built for, right? And optimized for. And what the drilling techniques have been optimized for. So Forge is about, in part, experimenting with drill bits and drilling techniques that can allow us to drill faster in igneous rocks. And so in this case, they're drilling granite, but I would imagine that translates over to andesites and basalts a lot better than some of the oil field or some of sedimentary bits. And also, it's not just the bit; it's the whole. If you've ever been on a drilling rig, the whole thing operates as kind of an ecosystem. Depending on how the bit is working, there are mud coolers, there are shakers, there are all these ancillary systems that operate in harmony to have the drill operating at peak efficiency. And when you change one element of that, you often have to change the others to adapt to. For example, if you're drilling a wider hole, which is often the case in geothermal, we drill, because the fluid is much less valuable per volume, we have to drill a much bigger, like we need a fire hose instead of a garden hose, is what my analogy would be to an oil well, or maybe a fire hose as compared to a coffee straw. So an oil and gas well might be finished at, 6 centimeters, whereas a geothermal well will be 30 centimeters, or more. And that is a much larger volume of rock that you're taking out. And so now you need all of the things on your drill to be larger gauge. You need your shakers to be able to process more to take out the drill cuttings. So every time you make an adjustment on these drills, there's a lot. It's got a lot of downstream effects that you need to make a bunch of adjustments for. So part of Forge is optimizing drilling and drilling techniques for different environment for more typical geothermal environments, and part of it is also to once those wells are drilled, to try to figure out how best to fracture. And again, the fracking techniques that we are basically adapting from oil and gas were pioneered in different kinds of rocks with different concerns. So, a lot of the fracking was pioneered in shales, where they want to extensively fracture the shales, but you don't want the fractures to go too far outside of the shales and get into the sandstones, which might produce water. It's a bit of a delicate balance. And so a lot of these systems have been carefully and developed and optimized for a particular system. And now we're taking the overall idea and putting it in another system, and we're having to re-optimize them to get the effects that we want. They don't work quite in the same way. They still work, but they don't work quite in the same way, and you have to make a lot of adjustments. And so, so they're doing a bunch of work to try to basically frack between wells and run stimulation and circulation tests. So they can show that they can frack between wells, but then they're trying to frack between wells that are farther apart. They're trying to make sure that the fractures are not to what we in geothermal refer to. We don't want a short circuit, which is we don't want the water from the injected well to get to the produced well before it has a chance to heat up. So, and this all sounds relatively simple in concept, but in execution, it can be quite complex. And so this is basically a big research station to experiment with that. Do you know anything else about Forge that you want to add, Steve?
No, I think that pretty much sums it up. I think one general thing that shale gas fracking has brought about, which has been a bit of a game changer for potential EGS projects, is multi-stage fracturing. In the past, in EGS projects such as the ones that were done in Australia, you basically fractured one zone, you created one fracture, and the two wells connected, and you get fluid coming back too quickly, like Scott said, you want it to heat up. Now what they've got is this oil field technology, multi-stage fracking with proppants that keep the fractures open, so you can create these multiple sets of fractures that the fluid can travel through, and the heat transfer is much better, and that hopefully will be a big game changer for EGS. And Forge is testing that technology out.
That's a very good point, because that has shown significant advances. But one of the things that, it's often presented as though, oh, we'll just take this oil and gas technology and convert it over to geothermal. It's as if it's a sort of plug and play, like a USB dongle or something like that. And the reality is it's not quite that simple. There are some significant technical challenges in geothermal resources that are different enough than in oil and gas, where while the idea can transfer over, how you actually do it sometimes requires some significant engineering to get it to work. And one of the challenges is a lot of this technology for the multi-stage fracking and for drilling long horizontal wells, a lot of the equipment for that can't handle high geothermal resource temperatures. So it's when we get into, so we end up sort of pushing that equipment to the edge of its capacity to get the highest temperatures that we can. But there hasn't been much demand in the oil and gas industry to really push that equipment into higher temperature ranges. So an example of this would be downhole logging equipment. Most oil field downhole logging equipment is rated to 300 Fahrenheit, which is, I want to say, what's that, about 180 Celsius? Is that right? I should check this. 300 F2C. Oh, sorry, 150. It's about 150 Celsius. And then the highest rated stuff is 500 Fahrenheit, which is about 260 Celsius. But there's only a few sets of tools that are rated to 500 Fahrenheit or to 260 Celsius in the world. And Halliburton used to make some, and then they stopped making them, and now Schlumberger makes a few. But the point is that historically the market has been small enough that these companies really haven't put much effort into making really high temperature tools. And that's a big part of the challenge with a lot of the geothermal stuff, is because we're such a small market. We're hoping to become a much bigger market if we can crack some of these challenges. But because historically we've been such a small market, tool companies haven't put the R&D money into making tools that can operate reliably in the higher temperatures. And so this is one of the challenges of EGS, is to apply all these oil field techniques without essentially frying the very expensive tools that we use to do it, because then that kind of messes with your project financials if you destroy the tools in the process. And the U.S. Department of Energy has various funding efforts around trying to encourage companies to build technology for these techniques that can withstand higher temperatures. But it's not a trivial thing. It turns out going over 150C with electronics is pretty difficult, and no one has a great cheap way to do it yet. But that's one of the significant challenges. And then there are a few other challenges as well. And so this is one of the things that comes up a lot. You'll see a lot of examples in Unconventional of oil field execs saying, "Oh, we've got this great thing in oil. Geothermal should just use this," as if we didn't know about it. And there's usually either financial or technical reason that we didn't just grab it off the shelf and give it a go. And those are the areas where you can make great strides. I think, in many ways, is overcoming those specific technical challenges to taking those techniques over from oil and gas. It's like if you can get the tool that does this to be temperature resistant to 100 degrees higher, that opens a lot more geothermal resources that you can work on. Anyway, I just wanted to make that point because it's a common thing that comes up with, in my experience when working with folks from oil and gas, where they're like, "Oh, you should just use this," and it's like, well, it's not quite that simple. There's usually a good reason that we're not using it already, and it's not to say that those issues can't be overcome, but it's not as simple as just sort of waving a magic wand. Okay, next slide. So the Fervo Energy Project Red, is quite interesting. So what they did here is they went to the Blue Mountain geothermal field, which was it's a convective hydrothermal, a typical hydrothermal resource. Well, a bit atypical in that it was a blind geothermal system. It had no surface expression, and it was found by accident by folks who were looking for minerals. They were drilling mineral exploration holes, and they kept getting hot wells and wondering about that. And then they realized they were drilling into a geothermal resource. And here you can see that the Blue Mountain field is these yellow wells, and that's kind of where the convective geothermal resource is. And what they did down here is these blue wells, they drilled an observation well, and they drilled a producer and an injector. And they did these long laterals. And I thought this was actually the first time that this had been done in a geothermal setting, but I was talking to Bill Cumming about this a few weeks ago, and he pointed out that they had actually done this in New Zealand back in the day. I can't remember which field, but it was something that basically they had proved that they could do it, but they didn't think it was economic and worth continuing. And they weren't doing all the fracking. I wish I could remember the
Yeah.
name of the project that had been done in. Do you know?
No, and yeah, I guess so. I can think of projects where the lateral
Mm-hmm.
distance that you go is similar to that, but the angle and the inclination, so going almost horizontal,
Okay.
I've not seen that
Wasn't.
anywhere else.
Okay. And
Yeah.
maybe it hasn't. We didn't get heavily into the details, but typically in geothermal, when we do directional wells, we have a lot less throw. And if you look at the beginning of these wells, like where the cursor is right now, if you were to sort of end that there, well, no, put it back where it was at the bottom of the curve. Yeah. If you were to end that sort of down there, that would be your sort of typical conventional geothermal well ish. What happens basically is you drill straight down until you get all of or mostly straight down until you get all your surface casing in and you're sure that you can control the well. And then you basically do your directional work between the bottom of that surface casing and when it gets too hot to run your directional tools anymore. And that can vary because as long as you're able to maintain circulation, you can keep your directional tools fairly cool. But once you hit, a big fault or something and you lose circulation and you no longer have the ability to cool your directional tools, conventionally at that point, we pull the directional tools and we drill the rest with what we call dumb iron, which basically just means stabilizers and a drill bit to maintain the angle of the hole, but you can't do additional directional work. So these laterals rely on the ability to maintain circulation while you're drilling the whole lateral so that you can keep your directional tools cool enough to not fry. So it actually works better. So in this case, if you can zoom back out, you can see what they're doing here is they've decided to drill down into a portion of the field that they had discovered with 41, 27, and 86, that down here was basically impermeable. It was still hot because it was being heated by being next to this part. So it's sort of like, imagine putting your hand on the side of a boiling pot. It's hot on the side too, and if you were to leave something sitting next to that boiling pot while it's hot, that would also become hot. But they didn't have the permeability, which in some ways is an advantage because it allows you to drill these long laterals while maintaining circulation. But then you frack between the two. And so they were basically, this was an experimental project to see if they could execute a multi-stage frack job between two wells, if they could drill these long lateral, oil and gas type wells and execute a multi-stage frack job between the two. And they were successful. And these wells were relatively expensive compared to a conventional geothermal well, and they, not huge producers, but they proved that they could do this in a geothermal setting. But I guess I would caution in that they definitely made significant technological advances in this project. But at the same time, when you read the articles about this, a lot of them are a bit promotional in nature and sell it like, I read a number of articles that basically said, oh, the first ever wholly EGS project with a power plant and everything. And I was looking at that thinking, well, they already had a power plant for a conventional system. Like, they didn't, these wells did not pay for themselves, nor did they pay for a power plant and all the transmission. They basically drilled them, tested them, hooked them up to the power plant that exists for this, which had excess capacity, and demonstrated that they could make power out of this, right? But I don't know the exact budget for these wells, but through the grapevine, I heard that they cost about twice as much to drill and frack as a regular, as a typical Nevada on a basin and range well, and they produce, I think, 3 or 4 megawatt, which is a little below what you would want. So they're an advance for sure, but they're not, it's not quite. It's sort of how to put it. They're early in the marathon and they're doing well, and they should be proud of that. But there's quite a bit to go still before it's finished. And so now they're taking this concept down to near Roosevelt Hot Springs, near Forge, and trying to do it at a larger scale. One of the big challenges between these two wells is they're drilled quite close together, and it will only, like, they haven't been running them that long, but over time we're going to see, do these wells short circuit? Do they cool themselves off too quickly? Part of the reason they ran them so close together is because they wanted to be sure that they could reliably connect the fracture systems. But at the same time, then you run the risk of short circuiting your wells, because in a conventional geothermal reservoir, when we run tracer tests to see how our injectors and producers are connected, if you're getting tracer test results that show, only a few days or only a few hours that it takes for the tracers to get from the injectors to the producers, that makes people nervous. You want long periods of time for them to make it back, or for them to never make it back, and still maintain pressure support. So, this is basically step one, and it's definitely a like, I don't want to take anything away from them in the sense that they did something new and they managed to get it done, but there's quite a few more steps left between this and a commercially viable project. And one of them is that these wells are dependent on this field for this temperature at such a shallow depth. If this geothermal field weren't here, in order to get the temperatures that they do with this, they would have had to go quite a bit deeper, and then the wells would have been correspondingly more expensive. So, as you can probably imagine, it makes logical sense to start experimenting with this kind of technology on the margins of existing geothermal systems, where it will, where it's economically favorable, where the temperatures are relatively shallow. And so they should, it's a sound approach to do this, but they're going to have to get these to be much more efficient and much more cost effective before they can deploy them away from conventional geothermal areas. You want to go to the next one? So I think that the first a bit of potential for Indonesia, I mean, obviously there's still a lot of conventional systems in Indonesia that have not been developed yet. And it's a part of how challenging they are, and where they are relative to population centers and all that kind of thing. Like sometimes you have great systems that require a ton of transmission to get where the people live, and then that affects them. But I think if you look at Fervo, where they started with sort of mining what I would call the conductive halo around a convective system. I think that's what you would start with in Indonesia as well, because you have a lot of convective systems that are very high temperature. And you have the transmission there. Like there's all kinds of reasons to do that, where you're basically expanding the capacity of a convective field. And that's going to be probably where it's most cost effective initially, because you've already paid for your power plant, your transmission, et cetera. And it's a lot cheaper to add additional capacity to an existing power plant than to build one from scratch. So I think that's, one of the technologies where, Indonesia has some of the most prolific geothermal fields in the world, and they, are quite hot, and some of them are going to have a significant conductive halo around them. They could probably be exploited. So I would start with that, because the infrastructure is already there. And then most of these geothermal fields are in, you can see that they follow patterns along areas with already high geothermal gradient. And so you can probably infill in between some of those with EGS projects, where they have most of the conditions that are needed, and particularly the heat. And so I think that's how it's going to start in Indonesia. Are there, Steve, do you know if there are, I'm trying to think, there are some areas of Indonesia with significant sedimentary basins, right?
Yes, yeah, and I've got a slide on that
Okay, perfect. We'll
towards
get
the
to
end
that
of my
then.
section. Yeah.
Yeah. Okay. Vicky, what's the best exploration strategy on an area with no surface geothermal expression? Boy, that's the magic question, huh? I think the play fairway kind of analysis stuff is actually pretty valuable. Looking for areas with favorable conditions, like extensional environments, where your efforts to create fractures will be, how to put it, like if you're in a really crappy compressive setting and you're trying to create fractures, it's going to take you a lot more work and a lot more money and energy to create a fracture system than in rocks that are in a more extensional environment, because you really want to be triggering fractures that are on the border of happening themselves. That's your sort of best case scenario, than to try to fracture something that really doesn't want to be fractured. You want the earth to be doing most of the work. So I think looking for the right kind of tectonic settings, and the coincidence of that with heat is your strategy. How about you, Steve?
Yeah, absolutely. And thinking of targeting geologic environments that are likely to have high heat flow. So, I have a slide in here that has heat flow versus geologic setting, and back arc basins like the ones that are found in Indonesia, because it's being pulled apart, it's extensional. The crust is thin, so the gradients are elevated, so you get higher temperatures nearer to surface. Plus, you also have the extensional environment. So yeah, looking at really geological environment, and then on a field scale looking at structural mapping and trying to come up with a structural targeting based on that.
Yeah, so I've been talking too long apparently. I'm not that familiar with Wying Windu personally. Are you, Steve? It's been
No,
10 years since I
not
looked at it.
massively.
I would say Wying Windu, like a lot of geothermal fields, EGS's best potential would be in the conductive halo around it. You might be able to stimulate wells a little bit within it, but it's really challenging because even a not great geothermal well has a lot of permeability, and it takes fracturing one of those wells is quite challenging. Except for, you can inject on it for a while to cool it and use thermal fracturing, but that takes quite some time and could screw up your whole reservoir management plan. So it has to be done carefully. And here it says
Sorry, Scott and Stephen, for the interrupt. I just want to remind about the time. It's still
let's
20
move over to
minutes left.
let's move over to
Okay.
Steve's. All right,
Yeah.
this is you, Steve.
How much time do we have left?
20 minutes left, Steve.
Okay, no problem. So we've touched on these subjects already, but the basics of sedimentary systems is that we are flowing water through porous sedimentary layers. They are either porous or they can be fractured and casted carbonate reservoirs. The existing geothermal plants that make use of sedimentary resources generally low temperature below 150, but there are resources up to 250 Celsius. And you can see here on the graph on the right, different temperatures for depth for different heat flow levels. So to get in the temperature range that we want at 3 to 4 kilometers depth, 150 to over 200, we need to have heat flows of over 80 milliwatts, sorry, per meter squared. And over 100 is preferable. So there's plenty of places in the world where that occurs. Next slide. So this was an interesting paper that came out a couple of years ago, looking at global heat flow data in a number of different ways. And the first graphic on the left here shows the geothermal gradient versus the continental crustal thickness. So I think, as Scott was saying before, high heat flows are associated with areas where the crust is thinned, and they found quite a sharp cutoff of about 28 kilometers, where below that you get pretty low, or thicker than that, you get pretty low geothermal gradients. And on the right here, we have different tectonic settings. So the highest geothermal gradients are found in oceanic. We're not going to be able to extract out of those, so we can write those off really. but back arc and fore arc basins within subducting zones, and that makes some sense because both are extensional environments, and there's thinning of the crust, and so hence high heat flow. Rifting environments can be good. I'm a bit yeah, I think I would have thought rifting would be a little bit higher than that, but maybe there's a problem with the amount of data that we have in rifting zones. Strike slip zones are not too bad as well, and then the rest are pretty low geothermal gradients, and I've put in a dotted line there of 75 degrees Celsius per kilometer. So that's to get you to, I think, 180 Celsius at 2 to 3 kilometers, in that range, which is what we're targeting. So we're really probably looking at back arc, fore arc basins, strike slip, where there's transtensional basins that are formed, and there's a number of those in Indonesia. And I would say young rift settings as well. So heat sources, just the general heat coming through from the center of the earth, but there can also be recent volcanism that elevates gradients. And in Australia, radiogenic heat from granites, so the decay of radiogenic elements produces heat, and that's a heat source. And then to extract the heat out of the rock, we're looking for porous and permeable layers. So we're looking for clean sandstones, casted or fractured limestones within the sedimentary basin at the depth where the temperature is just right. And yeah, a challenge is that porosity and permeability are generally decreasing with depth. So again, porosity and permeability can be a challenge. Next slide. Okay, so probably one of the areas of highest potential being in the Western US. It's an area of back arc basin and spreading, where the crust is generally quite thin, and we get high heat flow and over quite a large area of the Western US, shown in the map on the left here, which is the temperature at 4 kilometers depth. So you can see quite a large area of over 200 Celsius, over 175 Celsius in the Western US. And on the right here, we've got a map from a study that looked at the existing basins in the US where we have good data on porosity and permeability, and good data on temperature as well. You know, what is the prospectivity of those areas? And I've put a star on the ones that they found to be good prospectivity. So I think temperatures of over 160 and permeabilities that were high enough to get decent flow out of. So yeah, the area of those basins with the stars on them is huge, 3 million squared kilometers. And if we use the power density method, which is a simple but widely used method of estimating the geothermal resource capacity. If we use a value of 5 megawatts per kilometre squared, which I've taken from a sedimentary geothermal project, that adds up to 3,000 gigawatts. So that's 3 times the US installed capacity. So it's not to say that sedimentary geothermal will ever get to that kind of capacity, but it just demonstrates that there is that large potential there. It can be a significant player in the electricity mix. Next slide. Okay, so this is probably one of the best examples of actual sedimentary geothermal projects that are operating currently. This is in Germany in the Molasse Basin, which is not far from Munich. You can see Munich in the middle there. And there's 11 sedimentary resource geothermal plants that add up to about 47 megawatts, which is not too bad. The installation of these and why they kind of work is driven more by the high power prices in Germany. And that's driven in turn by a really strong push to renewables. So with higher power prices, you can do more. It makes the economics work out better for deep drilling and lower temperature resources. So there's a combination of both power and heat projects. The power ones tend to be more in the south where the temperatures get hotter. All of the resources are within the Marm limestone, which is a karsted and fractured carbonate formation that at about 2 to 5 kilometers depth. And they use seismic reflection widely to target high permeability. And there's some pretty impressive things that you can do with seismic reflection in sedimentary basins. You can see meandering river channels of high porosity, 3 kilometers depth with seismic. So you're able to target high permeability better, I would say, in sedimentary systems than you are in, say, an EGS granite type system. And the temperatures they're utilizing here are between 110 and 160 Celsius. Next slide. Okay. So the graphic on the left is a bit of a stock take of, or both of these are a bit of a stock take of the wells that have been drilled in these German projects. And if we look at the power projects, which is the right-hand panel, you see the first try borehole. So the first time they drill into the reservoir, only 32% are successful. And the rest of them either have drilling issues or they have low yield, which is the same as saying low permeability. But then what they do is they drill a sidetrack, so they drill another well out of the existing well. So that saves you some money in terms of not having to drill another completely new well. And doing that gets them to 77% success. And then for the remaining ones, that if they go a third time, they get to 86% success rate with their wells, which is not too bad. But as Scott said, and it's no different in these projects, we are drilling to 3 to 5 kilometers with big borehole diameters. The cost of doing so is quite high. Another cost in these projects is they have downhole pumps, which adds to the cost, and it's also a parasitic load. So you need power to run those pumps as well. So the graphic on the right basically shows that with depth, the drilling issues and the permeability issues are related to depth. So as you go below 3,000 meters vertical is when you start to have problems with drilling and with permeability. But unfortunately, that's the depths that you need to go to get 150, 160 Celsius. So for power projects, yeah, those are the depths you need to go to, and that's the risk you have to take, and it's one of the big challenges. Next slide. Okay, so potential for Indonesia. I think there's great potential. Most of Sumatra, the back half of Sumatra has got back arc basins where the measured heat flow is high, over 100 milliwatts per meter squared. And again, this is my back of the envelope calculation, but if you take the area there of 225,000 kilometers squared of back arc basin, and using that power density of 5 megawatts per kilometer squared, you get a potential resource of 1,000 gigawatts, which is again many times the current capacity of Indonesia. Again, just showing that there is a big potential resource there. The challenge, of course, is getting it out, and I'm sure that not all of this area will be able to be utilized. Next slide. Okay, so this is a closer look at the central Sumatran basin, and we've got heat flow in the middle there, showing that we get heat flow values over 100 over pretty much all of the area, and some quite extreme heat flows. And on the right there, we've got actual measured temperatures from wells. And the best quality measurements are what's called drill stem tests. So they actually produce some fluid. So that's the green dots and the green lines there. And the other ones are borehole temperature, bottom hole temperature measurements, and those are corrected measurements. So there's a bit of uncertainty in them. So both of those together, if you project them down, you're getting temperatures of 150 to 250 Celsius at 2.5 to 3 kilometers depth, which is, very reasonable. There's actually a lot of conventional geothermal resources that have those temperatures at those depths. So pretty good potential in that particular area. Didn't really look into what the sediment thicknesses were or the porosity and permeability, but that would be the next question. You know, you've got the heat there, but do you have the permeability? Do you have some good sandstones or fractured carbonates? Next slide. Okay, so I wanted to kind of sum up by just giving my thoughts on what is needed to make sedimentary geothermal a significant player in the electricity market. So there's thousands of gigawatts potential worldwide, but so far developments have been tens of megawatts. So what do we need? So we really need to maximize the megawatts per well, because the well costs are high. And megawatts is really governed by flow versus temperature. So permeability and temperature. Well, it's not just permeability flow. So we can increase permeability by doing horizontal drilling. So just purely making the length of the well really long, so that the permeability that you intersect is much more. You can do hydraulic fracturing in sedimentary formations. There's chemical stimulations as well. And we can use the latest in seismic reflection to really target areas of high permeability. Another thing that could increase flow rates is improvement in downhole pump technology, particularly getting high flow pumps that are capable to over 200 Celsius. And I wanted to make a point here that small changes in temperature, they can seem small and insignificant, but they actually have quite a big effect on efficiency. So we've got the graph here of reservoir temperature or enthalpy versus the thermal efficiency. So this is the percentage of the thermal energy that gets converted to electrical energy. And this is from a database of worldwide geothermal power plants. And you can see if we go from 120 Celsius to 160 Celsius, we basically double our efficiency. So a lot of these projects that are targeting temperatures of 120, 130 degrees Celsius, it's really hard to do those projects because you need so much more flow to make up for the lack of temperature. So to me, the low-hanging fruit is really in areas where we have measured temperatures of 160, 180 Celsius at 3 to 4 kilometers depth. And mostly we need demonstration projects in these areas where we know we've got good temperature and we've got good thick layers of porous and permeable reservoir. So something similar to the Fervo EGS project, where someone stumps up 100+ million and we can drill multiple wells and test them out. And perhaps Indonesia is the best place for that. So I think that was the last slide I had.
Can I add one little bit to that last comment, which is just that I was talking to some folks about some projects in the Netherlands where they are basically doing deep sedimentary out of the lower, like they've got units that are in anticlines and synclines that in the high parts in the anticlines they're oil traps, and then in the low parts in the synclines they're producing water. And one thing they were finding was with compaction and cementation, they sort of had I think it was a sweet spot of like below 4 kilometers, you really started to lose your primary porosity, and so then it went into becoming an EGS project. And so it was sort of like you were looking for that sweet spot where you were over those temperatures, like high enough temperatures before you started, but there was a narrow band, and I don't have the details on that, and it probably varies from place to place, but where you get, high enough temperatures before you've basically gotten so much compaction that you've lost too much of your flow.
Yeah,
So
not
anyway, that was an interesting point that they had made. They had sort of calculated a sweet spot in there of about a kilometer thickness.
yeah, that's a good point. Also with temperature, you get more alteration, quartz growth, which lowers the porosity and permeability. And the project I worked on in Australia had that issue. That said, the basins that I showed before in the US, they basically narrowed down to ones where they had a lot of data on porosity and permeability and could show that, yes, they do have the permeability at the target temperatures that are needed. So there are places around the world where the right temperatures can be found and the right permeabilities naturally. And there is also the option, of course, of doing some fracturing and stimulation to make things better.
You want to address some of these questions in the
Yeah, sorry, I haven't been keeping up with the questions.
oh, it's okay.
Okay, so thank you so much, Steve and Scott, for the insightful presentations. Maybe we can enter the Q&A sessions, so the participants can ask directly the questions that we will ask to both of you. Maybe I will see the questions that already come to our chat box. There's a questions from Pak Ahmad Hidayah. Pak Ahmad, do you want to ask directly to the speaker or I will help you to read that questions?
Maybe directly.
Okay, please, Pak Ahmad.
Okay, first of all, thank you for the insightful session from Scott and Steve. I have a question. As we know that in Indonesia, Indonesia has various fault zone and subduction zone. Because of the location of Indonesia, as we call this ring of fire. So the question is, how could we know or investigate that this fault zone or the subduction zone could make or impact to geothermal potential area, and which factor that dominant effects for geothermal potential, and in that case for subduction and fault zone? Thank you. Do you get my question?
I think so. I mean, initially, like that tectonic setting is why Indonesia has a wealth of geothermal resources to begin with, because that's that subduction zone and the fault zone. What is it? The intra? There's there's a strike-slip fault that basically most of the volcanoes in Sumatra line up on, right? I can't remember
Great
what it's
Sumatra
called.
fault.
The Great Sumatra Fault. Okay, well, I should have remembered that. It's a clear name.
Easy one.
Yeah. I would say for these type of systems, your systems are already on that in the spot, the convective systems where all the geologic conditions are perfect. And so you could look at sort of along that same trend, along that same structural trend for EGS systems in places where conditions were a little less perfect, where basically you still have the heat flow, but you don't have quite the level of permeability because it's still probably similar. As to how that fits for sedimentary basins, I don't think they line up, do they? Or what do you think, Steve? They're more back arc.
Yeah, I mean, there's definitely a structural element to the back arc basins. There's going to be zones that are extending and zones that are coarse. So yeah, there's going to be an element of structural control there. And yeah, along the Great Sumatra Fault itself, there's a number of these pull apart basins, and there's already some geothermal fields that are associated with those Sewell. Yeah, there's a bunch of them. Maralabu is near one. So there could be potential within some of those pull apart basins, or perhaps at the bottom of the sedimentary pile of those sedimentary basins. Yeah, there is for EGS as well in Indonesia. There are also quite a lot of areas that have low permeability but high temperature. There's a lot of that found in Sumatra. There's an example I know of in Bali where must have been 5 or 6 wells drilled, but all of them were high temperature, 320 degrees Celsius, but low permeability, and a project couldn't be developed. So there's also already some tight systems around that could be developed into EGS systems.
Okay, thank you, Scott and Steve, for the answer. Maybe we will next to another questions from Mas Vicky Raichandra. Mas Vicky, do you want to ask directly, or I will help you to read the questions? Okay, I will help to read the questions. So, hi Steve, what data set did you use to create the heat flow map? Central Sumatra Basin, I think. Central Sumatra, this one, yeah.
So yeah, first of all, it wasn't me, it was the source down below there. And how it was done was using this oil and gas data. So this is an oil and gas basin. They drill wells. They're not usually that interested in temperature, but they usually take temperatures at the bottom of the wells, and they take those at certain times after the circulation has stopped. And so what we're seeing there is on that graph is the bottom hole temperatures. They also do drill stem tests, which is actually flowing some water up the drill stem and measuring the temperature. So they use that temperature data. They have some thermal conductivity data. You can also just use typical values for the geology, and they put those two things together and they come up with heat flow. Conductive heat flow, by the way, I should have said at some point, is just the geothermal gradient times the thermal conductivity.
Okay, thank you, Steve and Scott. Maybe one questions for this webinar from Ms. Gersan Salihin. Ms. Gersan, do you want to ask directly, or I will help you to read the questions? Okay, for all the participants that already write your questions in the chat box, maybe you can send to us, so we will send the questions that are still not answered to Scott and Steve. And the answer we will share on the WhatsApp chat. Okay, maybe I will help to read Mas Gesan questions. Okay. Thanks, Steve and Scott. Thank you for the presentation. A question. Is the hydrothermal mirroring marking such as epidot for high temperature reservoir or smectite in the clay cap also applicable in the AGS and sedimentary system?
I think somewhat, but I think they would be generally less developed in when you don't have the permeability to flush. I mean, so the temperature and pressure conditions would still be there, but when you're not flushing a constant source of mineral laden water through, I would expect that they wouldn't develop as strongly. What do you think, Steve?
Yeah, I think that could be true for some EGS systems. Although I'm just trying to think, are there any examples where they have an EGS system that doesn't have a cap over it of some sort? Because I mean, the one in Cooper Basin has a thick sedimentary basin on top of it. Because you still, yeah, I mean, I guess there could be a case still where there's just granite from surface that's just tight, completely tight, and that's hot. And you could have a system in that is theoretically possible. For the sedimentary systems, yeah, I do think you need some low permeability to stop fluid from flowing down, cold water from flowing down. And usually that is like in conventional systems, smectite rich, clay rich intervals that are the low permeability layers. And then beneath those you get the clean sandstones and the carbonate layers that form the reservoir. And those reservoir zones have to be low clay. Otherwise, yeah, you get plugging of the permeability. So those zones usually either have just not much clay at all, or they have clays that are illite or chlorite that don't plug permeability as much.
Well, a follow-up question to that for me is that I've always imagined, and I may be incorrect about this, that in the sedimentary systems, those clay-rich intervals, basically the mudstones, are more of a primary depositional thing rather than like hydrothermal alteration. Whereas in and in a conventional convective hydrothermal system, you're talking about rocks that were primarily volcanic and then have been hydrothermally altered. But I just assumed that. I don't know if that's actually true. What do you
No,
think?
I think you're definitely right. Yeah, these are in these sedimentary basins, dominantly sedimentary clays. There can be hydrothermal clays. And you do see in some systems in the US that the two kind of overprint on each other to get extra high smectite clay content. But yeah, no, in these sorts of systems, generally it's going to be sedimentary sources of clay.
Okay, thank you so much, Stephen Scott, for the great presentations for today's webinar. We all the participants is happy for gain new knowledge and insight from both of you. But however, due to the time constraint, we must close the Q&A sessions. So for all the participants that still have other questions, feel free to give to Enerka team by this Zoom meeting chat, or you can ask directly to in group WhatsApp. And for today, summarize for all the presentation materials. So the geothermal system is not about not only the conventional system, but also there are unconventional systems that still we need to develop. However, there are still a challenge in develop those systems, such as the permeability and in economically aspect. So maybe this is the wrap up for the sessions. Back to the MC. Anissa, are you here? Oh, sorry, Tracy. For the Enerka team, please.
Okay, thank you, Serena. So, everyone, first, I would like to say thank you to Kak Serena and also for Steve and Scott for the amazing material. But before that, before we conclude today's webinar, we would like to remind all the participants to fill out the feedback survey on the screen to receive your certificate. Maybe I will you once and I will send the chat box. So only participants who will receive the webinar. So everyone, next, on behalf of the Enerka team and also APG SC, we would like to our esteemed speaker. So for I would like thank you for the amazing presentation. Maybe we can take a picture first, Scott. Okay. I will the picture. So 3, 2, 1. Okay. Okay, so much. For the next one, our speaker. So we can take a seat. Okay. 1, 2, 3. There's a bad connection here. Okay. Thank you so much. Thank you so much. We once again like to say thank you to our knowledge and also insight with us. And next, for those turn on your cameras, please to turn on your take a group photo together. Maybe everyone we can open our camera so we can take a picture together. Yeah, everyone. Okay, I think everyone is already open their camera. So I will leave the documentation. All right, everyone, get ready. In 3, 2, 1. Okay, once again. 3, 2, 1. Well, everyone, thank you very much to the participants and also to our speakers who have followed the event from start until finish. We would like to apologize for any shortcomings during the session, and we hope this knowledge shared has been valuable and also beneficial to everyone. So with that, we bid you farewell. Wassalamualaikum warahmatullahi wabarakatuh. Thank you, everyone. See you on our next event. Thank you so much. Steve. Thank you so much,
Kasih.
Thank
Scott.
you, Scott. Thank you,
Bye.
Terima
Steve.
kasih.
Thank you, everyone.
Terima kasih.